Chapter 6, new section. This lesson, we're going to talk about how to solve a system of linear equations only by graphing. Alright? I'm going to show you how to do it in the calculator as well, so that you have a pretty good understanding of how this works. But before we begin, first of all, let's talk about what is a system of linear equations. Have you heard this term before? One person has? Okay, no one has. Alright. Oh, we have. Alex, you have two. Okay. So, a system is generally denoted with these little brackets here, but sometimes the book doesn't use them. So here's an example of a system of linear equations. Y equals 2x plus 4. And here's another one. Y equals x plus 2. So really, the definition for us, a system of linear equations is just two or more, because you could have 3 or 4 or 5, but we're going to usually deal with two. Two or more equations solved at the same time. That's all it is. Solved at the same time. And since we're talking about linear equations, you can assume that the equations that I'm talking about are linear. Okay, so two or more equations solved together at the same time. Alright? So, here is an example of a system of linear equations. And the thing that we're supposed to do with this is we're supposed to solve it. Well, how do you solve two equations solved together at the same time? Well, that's one method, but we're solving by graphing. Yes, Lewis. I mean, Will. So yeah.
So you would, well, I believe like you make them both in place of or just graph them out.
Yeah, we're just going to actually graph them out. Okay. So let's actually do that, but let's do it the quick way. Let's do it using fluid math, since I already got it set up for you. Okay. Here's the quick way. Here's 2x plus 4, and then x plus 2. So if I want to graph both of these, I'll put them both on a graph. And this is the picture that I would have right here. And I'll maybe zoom out a little bit like this. And here's what I'm going to do. I'm going to take this information, I'm going to copy it, I'm going to put it back over to our lesson so we can talk about it. Okay? So here we go. Here is the system graphed together at the same time. So let's talk about it. What do you notice about these two lines here? Anything that you see or notice? Yeah, Alice. You're saying the solution is negative 2, 0. What do you mean by that? So, okay, what does it mean for a system to have a solution? You're saying that this point right here is the point negative 2, 0, and you're saying that this is the solution to the system. Why would that be the solution to the system?
Because if you plug it into both equations, it turns out that they can be solved.
Exactly. So what she said was, if you take that point and you plug it into both equations, it'll work out. So what the idea that we're looking for here is we're looking for a point that's in common. What is the one point that's in common to both equations at the same time? That point happens to only be negative 2 and 0. So what I mean by that is if I go back in and I check, if this is my x value and this is my y value, if I go back and check, is 0 the same thing as 2 times negative 2 plus 4? So is 0 equal to negative 4 plus 4? Does 0 equal 0? Yes, it's true for the first equation. Let's check the second equation. I'll use a different color to show you the difference. Again, I'm checking 0, negative 2. So is 0 equal to negative 2 plus 2? Does 0 equal 0? Yes, that's also true. So, negative 2, 0 is the only point in which both of these equations have in common at the same time. Therefore, the solution to my system is that one single guaranteed point. That make sense?
So the solution is always.
Okay, ladies and gentlemen, your calculator is a great tool for solving systems using graphing. Let me show you how it works. Right now, my calculator still has a bunch of stat plots in it like we had before. So I'm going to go ahead and turn my stat plots off because I'm not interested in plotting anything anymore. So to do that, I just hit second y equals, and I'm going to go down to option 4, which says plots off. And then I push enter one time, And then if I push enter again to confirm that, it tells me that, okay, your plots are now off. The calculator said you're fine to go. Then I'm going to go to y equals, and I'm going to make sure that there's nothing inside the y equals button. Mine happens to be that line of best fit that we did in that last example. So I'm going to hit clear right now, and then clear everything out. Okay, so this now leaves me the ability to graph my system of linear equations. So notice that when you're graphing something in your calculator, it always has to be in the terms of y equals something. So if we had an equation like 3x plus 2y equals 9, we would have to solve that equation for y by itself. So it's important to know that if you're going to plug something into the calculator, okay, you have to solve it for y. So luckily for us, in this case, both of them are already solved for y, so I can plug it in. So I'm going to punch in 2x plus 4. So I punch in 2. The x button is right here. It's the last red button that I pushed. It's the like 1 over and 1 down from the second button. That's your variable button, x. And then I want plus 4, so hit plus and then 4. So now I have entered into the calculator y equals 2x plus 4. And your calculator has a bunch of different zooming features, and the one that is used most often is called zoom 6. So when I hit the zoom button right here, the option that says number 6 says Z standard, and that means for zoom standard. So if everyone just pushes zoom 6, we should all be looking at the same screen. So my screen should be matching what your screen looks like if we all push zoom 6. Okay, so everyone's good there. Now notice that we have graphed the first line, 2x plus 4. Now we also have to graph the second line, x plus 2. So we're going to go to y equals, and I'm going to move my cursor down to the next line where it says y sub 2. That means the second y equation that you have. So I'm going to punch in that as well. I'm going to punch in x, and then plus, and then 2. Now, your calculator, if it's this colorful one, it will automatically change the color of the graph. So my first one will be blue, my second one will be red. So I kind of know that ahead of time. It's kind of nice. So I'm going to go ahead and hit zoom 6, make sure we're all looking at the exact same thing. And there's my first line, 2x plus 4. And look, there's my second line, x plus 2. Okay? Let me pause right here and make sure we're all on the same page. All right, so now that we have our two lines graphed, all right, we want to figure out the solution. And we know that the solution is already going to be this because we checked it out. We know the solution is negative 2 comma 0 because we graphed it in fluid math, right? So how do we figure it out in the calculator? Well, here's what you do. You hit second, and you hit trace. When you hit the second option, you're activating the blue word above the word trace, which is calculate. So second trace, okay? And we have a couple of options for us here. Look at option number 5. What does that say? Intersect. That's what we're interested in, right? Because we know that the intersection of two lines is the solution to the system of linear equations. So we're going to go and hit option number 5 right now, okay? When you hit option 5, you should see somewhere on your screen what I call the blinking butterfly. See, mine's like a little black blinking butterfly. Alliteration aside. Kind of funny. Never mind. Anyways, so look, I want to figure out where these intersect. Okay, now look. The calculator is actually asking me a question right now. It's asking me, like, is the little blinking butterfly on the first curve? Now, we happen to have lines, but the calculator just uses the word curve anyways. So, you guys, is it on the first line? Yes or no? It is, yes. So all you do is push enter. Okay, now the calculator is asking me another question and saying, hey, is the blinking butterfly on the second curve? And is it, you guys? Yes or no? Yeah, the calculator is pretty smart in that sense, okay? So you push enter again. All right. Now the calculator plays a game with you, and it says, do you want to try and guess where you think the intersection is? If you're feeling happy and you'd like to guess, you can just move your cursor to where you think the intersection is. Okay? And I think the intersection is about there. That's my guess. Okay? You can guess if you want. You don't have to. Okay, once you think you have where you think it is, or if you just want to skip it, you just push enter again, and the calculator automatically calculates the answer for you as the intersection of, look, oh, there it is, 2, 0, Sweet.
I thought the
Okay, ladies and gentlemen, here we go. Let's talk about types of linear systems that we are going to encounter in this section of our Algebra 1 study, okay? There are two types of systems that we need to concern ourselves with. The first type is called a consistent system. The second type is called an inconsistent system, okay? So that's our first order of recognition, whether or not we have a consistent system or an inconsistent system. Consistent means that there's an answer. Inconsistent means that there is no answer. Okay, we're going to talk about that more in a little bit. But let's just focus right now on consistent. If you have a consistent system, there are two different types of consistent systems. And noticing I've labeled them A and B off on little spears for you, right? The first type of consistent system is known as independent. Okay? And that basically means that there is only one solution. Okay? The example that we did together in box number 2, this right here is an example of a consistent, independent system. Why is this a consistent, independent system? Because it has a solution and it only has one solution. All right? Meaning the point -2, 0. Now, there's another option. It could be a consistent system, but it could be a dependent system. And that means that there are infinitely many solutions, and we will take a look at one of these in a minute, okay? So the first idea you have to understand, there's two types of systems. It could be consistent or inconsistent. If it's consistent, it can be subcategorized as to independent or dependent, depending on whether or not there is a solution to the system. I will give you an example of each in a second. Now, the other one is inconsistent, right? If it's inconsistent, we just say that there's no solution. Okay, let's talk about an example of each one of these, okay? Let's do a consistent independent system. We're going to do y equals x plus 2 and y equals 3x minus 2. Let's get some practice graphing in our calculators and solving using the graphing calculator, okay? So let's go ahead. So I'll pull this up. I'll go to y equals. I want to clear out my first two just by pushing the clear button. I want to go back to the first y, and I want to enter in x plus 2. So go ahead and punch in x plus 2. Then I also want to punch in my second y, which is 3x minus 2. So let's punch in 3x minus 2. Pause right there and make sure we're all on the same page. We all good?
Yes.
Okay, we're all good. Good. From here, let's all hit zoom 6 to make sure that we are all staring at the same picture. Okay, here's an example of a consistent independent system, okay? The reason this is consistent is because it has a solution. The reason it's independent is because it only has one solution, right? I can see clearly that it only hits in one spot, right? What do you think that spot is, by the way?
I think that
Looks like
is
2, 4.
2, 4? Let's see if you guys are right. Let's go second, calculate. And let's go to intersect, option 5.
Yes,
It's
the
2,
first
4.
curve, yeah.
And then hit enter, enter,
I'm not gonna guess.
enter.
I'm gonna guess.
Oh my gosh, you guys were totally right. 2, 4. Absolutely perfect.
I'm a genius.
Okay. So this one. Okay, so let's go ahead and talk about a consistent dependent system. All right, we want to make sure, we want to graph these in our calculator. But notice right away that this particular equation is not solved for y. So we have to solve it for y if we want to plug it into our calculator, right? So what do? Okay. So I'd say 2y is equal to x plus 2. Then what?
Y equals 1 half x.
Divide by 2, divide by 2. So y is equal to 1/2 x plus 1. Hey, wait a minute. That looks exactly like that system right there. So what does that mean?
They're dependent and consistent, and they intersect on infinite points.
Okay, so let's take a look at their graphs, okay, individually. So we had these two equations. I'll write out the original way. 2y, sorry, it was minus, right, huh? 2y minus x is equal to 2. And the other equation that we had was y is equal to 1/2 x plus 1. Let's put both of these on the graph. Wait a minute. Why do I only see one line? Because they're the same. Okay, they're the same. There are two lines. That's one's right on top of the other, right? So look, this has an infinite amount of solutions, right? No matter where we go, this thing has an infinite amount of solutions. So let's take this and bring it over to our notes so we can do a little comparison here. Okay? So what's the difference between this graph here that we've just looked at and the one before it? They're both consistent, but what's the difference? There you go. So that's what I meant back over here when I talked about one solution versus infinitely many solutions. Do you understand now? All right, the world makes sense. Isn't that awesome? Okay, our last and final example is an example of a system that is known as inconsistent. So we're wondering what this graph's going to look like. So we wrote them down over here in Fluid Maths as a quick little graph here. Let's sketch them out. And what are we noticing here about these two particular graphs, you guys? They are parallel. Okay, so let's bring it back to our notes and let's talk about it. Okay, here it is. Here's our notes. Now, what makes this an inconsistent system? Why is that word used? Because they have no points in common, right? There's no single point that makes the blue line and the red line equal anywhere in the plane, no matter how far out we move. So that's what makes it an inconsistent system. Okay, so here's all three of these together in one box so we can see. So we need to be able to discern between a consistent independent, meaning there's one solution, a consistent dependent, meaning that there's infinitely solutions, and inconsistent system, meaning that there are no solutions whatsoever. And we also need to be able to graph these into our graphing calculator and graph them by hand, but the calculator is a little bit more fun since we already graphed by hand, and determine their outcomes.